Today we're gonna have Professor Alexander Fradkov. The title is Speed Gradient in Modeling, Control, Adaptation, and Learning. At some extent, this is a similar presentation that Professor Fradkov gave in his plenary in Alcos, in Mexico, in two months ago. And I think uh, all of you will enjoy because you bring some nice history and okay, up to date concepts that we can use in these different uh, areas like modeling, control, adaptation, and learning. So, Bing, I would be pleased if you can formally introduce Professor Fatkov with his bio, right? Thank you.
Okay, so I have the honor of introducing Professor Alexander Fradkov. For many of us, he doesn't need an introduction, but just a very, very brief overview. So he, as you know, is a distinguished researcher in control theory and cybernetics. He received his diploma degree in mathematics from Leningrad and now St. Petersburg State University in 1971 under supervision of Vladimir Yakubovich. And then his PhD degree in 1975 in technical cybernetics and DSc degree in control engineering in 1986. He currently leads the Control of Complex System Lab at the Institute for Problems in Mechanical Engineering of the Russian Academy of Science and is a professor at the Department of Theoretical Cybernetics at St. Petersburg University. So he's the author of more than 800 papers, 18 books, and 12 patents, and is a pioneer of the field of cybernetic physics. So he received a large number of awards. He's currently a IEEE Life Fellow, IFAC Fellow, and received awards including Andronov Prize and IFAC Best Paper Award for Annual Review in Control. So, Alexander, time is yours. Do you wish me to play the video now?
Just a minute, I say a few words. Dear colleagues, dear friends, it's my honor and pleasure to make a talk at this seminar, and I would like to thank Tiago and Bing for nice introduction. And actually, this committee is my native committee. I'm working in adaptive and learning control for a long time, more than 50 years. And actually, I was chairing this committee for 6 years till year 2014, the IFAC Congress in South Africa. And before I start lecture, I decided to make an experiment. And before this experiment, I would like to give a few introductory words. I first show you the experimental setup. Please have a look. There are three rulers of different color, red, blue, and white, like colors of flags of some countries, and a nail. And these three pendulum are suspended from while axis. And now in my experiment, which I think Bing will show you now. We decided to do it in such way in order to avoid the possible disconnection in our lecture. Please, Bing.
I think it's muted, Bing.
Sorry, Tiago, can you hear my the sound in the video?
Oh, we don't have sound.
Was that all right?
No sound.
The sound in the video. Okay, I'll start play again.
Okay.
Just to make sure things are.
Please start again. Okay, if there is no sound, I can make sound myself. Can you hear me?
Yes.
Yeah.
You can hear. I'll comment. This beginning is the same. 3 pendulums of different color, different lengths. White is short, and middle is blue, and red is longest. And the problem is to swing up one pendulum and to keep 2 other pendulums not swinged up. And it's not easy because we have only one control with 3 degrees of freedom. Now, first I start with white, with shortest pendulum, and you can see that it is successful. This short pendulum is swinged up. And now next I try to swing the red one, and after some time it also swings up. And again, it's okay, but it's difficult for me to swing the middle. And this question which I going to ask the audience is that these 3 pendulums have different lengths. And the question is it possible to swing up to solve the same problem with one pendulum if all pendulums have the same length? They are identical. So I suggest you to think a little bit, and I start lecture, and at some time we may discuss this issue with the audience. Is it possible? And if it's possible, and when and under what conditions it's possible? So this is the end of it. Now I would like to switch to the presentation, to the lecture. Can I do that? Small stop. The title of the lecture is Speed Gradient in Modeling, Control, Adaptation, and Learning. I would like to tell you about some approach to solve these problems. And I will speak about modeling in the end and start with control, adaptation, and learning. The plan of the lecture outline is as follows. I will first describe the basics of the speed gradient method, the problem statement, control algorithm design, some proofs. Then I'll be speaking about robustness of system with speed gradient algorithms, and special case control of invariance, which requires some discussion. Then I will speak about some examples and come to some extensions, Lyapunov-Bregman functions, speed gradient models of physical systems modeling, and other problems, non-smooth distributed systems, and so on. And now, before I start according to this plan, I mentioned that there are many publications related to the speed gradient methods, and I would recommend you a recent survey co-authored by Boris Andreevsky, who is my old co-author and friend, and this survey published in year 2021 has more than 200 references, and you can find everything about speed gradient method there. And now let us start with the problem statement. Let us consider the controlled plant were described by equation 1, where x is a state vector, theta is the input vector, which may be a vector of controlling variables or tunable variables in case of adaptation for control or adaptation. And the control goal is to achieve the asymptotically minimum value of some goal function, non-negative goal function. We need to achieve zero value asymptotically when time goes to infinity. A function q is given in advance. It corresponds to the technical or physical goal which we want system to achieve. So the problem is to find a control or adaptation algorithm, how to change theta with time in order to the goal 2 is achieved. The idea of speed gradient methods is simple. If we have a goal function, we need to decrease it, then why not to evaluate the derivative is speed, the speed of changing q according to the system, controlled system. And then after evaluating q dot, we evaluate the gradient, the second step gradient in theta of this q dot. And after that, we write down the speed gradient algorithm. The gradient, we change theta according to the, along the gradient of the speed. That's why it's called speed gradient algorithm. And we may change it in a differential form as a differential equation, or in a finite form as a finite equation. It may be considered as equation at each step should be solved. And here gamma is a positive definite gain matrix, and vector function psi forms acute angle with the speed gradient. So we actually, the idea is to change input variables in such a way that the speed of changing the goal function would decrease with time. In this case, eventually it may become negative, and if q dot becomes negative, then q itself will decrease. And eventually, under some conditions, we may expect that the goal will be achieved. And now I'll show you typical conditions under which the goal is really achieved for this method. First we need to introduce some assumptions. And there are four typical assumptions. First is regularity, type continuous or locally bounded conditions for the right-hand side of the equations involved. The second condition, second assumption is imposed on the goal function, is regular unboundedness of the goal function. Third assumption is convexity of the speed of changing w of changing the goal function. It should be convex in theta. Convex in theta is important conditions. And the final important condition is attainability of the goal, existence of some vector theta star such that the speed is negative if we substitute this theta star. The speed is negative and is principal achievement of the goal, achievability of the goal. But unfortunately, we do not know the theta star. It is unknown, both in control and in adaptation problems. And we need to design algorithm which does not depend on theta star. Theta star is ideal vector, but it is unknown. And under this condition, we can prove that some results for achievement of the goal. This first result, theorem 1, I'll show you under conditions A1 to A4. Then all the solutions of the system, the controlled system 1, 2, 3 with differential speed gradient algorithm are bounded. All the conditions, all the solutions are bounded, and the goal is achieved. This holds for all initial values for both for x and for theta. And the boundedness of conditions are very convenient properties that allows us with some example. I'll show you equation stands as part of the coefficients at the gain of the system. So adjustable gain is the adaptation problem, typical adaptation problem, adaptive stabilization, and the problem of control goal is correspond to the stabilization. It's just squared goal function is squared value of x, and with this function we evaluate q dot. It linearly depends in theta. Evaluating the gradient of the speed, we obtained x square, and we arrived at a well-known, familiar to many of experts in adaptive control algorithm, which depends square of right-hand side square over state of the system. And according to the theorem 1, the goal is achieved. And next, I would like to show you the idea of the proof of this result. The proof is based on introduction Lyapunov function based on the goal function. Peculiarity of this Lyapunov function is produced from the goal function. We take the goal function q and add some penalty term measuring the deflection theta input variable theta from the ideal value theta star. With this Lyapunov function, we evaluate its derivative and using conditions of the theorem, we show that it is non-positive, and which means that Lyapunov function values are bounded, and the Lyapunov the goal function is bounded, and the theta also is bounded, and all this means the boundedness of the whole trajectory of the system. And under this condition, we may prove that boundedness. This is the first part of the trajectories, and the second part, in order to prove it, we need to apply the Barbalat lemma. Check the uniform continuity of the integrand in this condition, and evaluate q will tend to 0 under assumptions imposed of the theorem. And so the proof is very simple, but the result is rather general. And note that if we have we are interested in studying finite form of speed gradient, finite form, not differential form, then the goal function itself is chosen as a Lyapunov function without any penalty term. And second remark is that we may design a combination of finite form and differential form algorithms like that. We call it finite differential algorithm. It may have properties good properties as differential form and finite form simultaneously. And, we often use this type of algorithm, but I have no time to discuss this in details. In the publications, you can find more about this issue. What is important is that such algorithms are very nice, but they are not very robust. It can be seen as an example. Consider again the same example as we started, a scalar example, scalar plant, but assume that it is influenced, affected by disturbance. F of t, F is maybe small, but it does not vanishing. And it is easy, can be seen even with arbitrarily small constant value of F, the trajectories of such a system, the disturbed system, may go to infinity. The value of theta may go to infinity. This unpleasant phenomenon was known long ago. Yes, this picture is taken from the book published in year 1981 in Russia. This joint book with my book with Professor Fomin and my teacher, Professor Yakubovich. And in this place, I would like to mention that next year, in the year 2026, there will be a centenary of Professor Yakubovich. We will celebrate it. This important event. This book was not translated in in English, but it was used by many people later. By now, even by now, people reference to this book. And now I can say that I would like I can provide you with results related to robustness of speed gradient. To this end, we need to modify the goal, achieving not asymptotic stabilization, but asymptotic bounded error for the system. The goal is formulated in equation 10. And we also modify the speed gradient algorithm itself. We achieve the parametric feedback, so-called, often called the sigma modification. For this case, such a negative feedback provides stability, can regularize the system, provides robust properties of the system under bounded disturbances. And I formulate you results, and the proof is very simple. I do not go in detail. Again, we use the same Lyapunov function and evaluate its derivative, and it happens that we obtained some ultimate boundedness of the system trajectories, and then evaluate the limit error. And I would like to finish this part with remark 4, which says that the conditions under which speed gradient method works can be interpreted as pacifiability of the system itself. It's condition of attainability of the goal is equivalent to pacifiability of the system. This is nice. It was published in our joint paper with David Hill, something junk, long ago in 1995. And now let me go to other problems. First of them is control of invariance. And its special case control of energy for conservative systems. Suppose we have a Hamiltonian system. H, it is a controlled Hamiltonian consisting of free energy, H naught, and the interaction Hamiltonian H1 times U. Yeah, U is a controlled variable, controlling variables. It may be forces, some fields or parameters. And the goal is to achieve the desired value of energy, H star. And we want to achieve it with a relatively small input. We want input to be small, and we want to have some non-local statement about the properties of this system. It is not so easy because of some peculiarities of this problem. It is not a stability problem, it is a partial stability problem. And anyway, we may apply speed gradient method to this problem. We introduce the goal function as a squared error in terms of energy. And evaluating Q dot and then the gradient of the speed, we arrived at the algorithm, control algorithm, which is proportional proportional to the error in terms of energy, but the gain is non-linear, and this is a well-known function free Hamiltonian and interaction Hamiltonian. So the following statement can be proved. I will not prove, but the first one is quite easy. And the first statement is that if Poisson bracket does not vanish in the area of initial conditions where Q, the goal function, does not exceed the specified value Q naught, if this value is not Poisson bracket not vanish, then the goal is achieved. The goal with this control algorithm, speed gradient algorithm in finite form, is achieved for any value of gamma, positive value of gamma. So the control may be big with large gamma, or it may be small, even arbitrarily small. And in all cases, the goal will be achieved. It's interesting. And the second statement, more subtle. If the Poisson bracket is vanishing in a countable set of the initial conditions omega, then there is an alternative. Either the goal is achieved, initial goal is achieved, or the state of the system tends to some equilibrium of the free system from the set omega. In the first part of the theorem, this set of equilibrium is empty, and then goal is achieved always. But in the second part, if it's not empty, it's a countable set, then there may happen that X tends to some equilibrium, to some of countable set of unpleasant solutions. But this is life. And this type of statement can be extended to more general case for affine in control system, for example. And here output Y is invariant of the system, like analog of the energy. It may be also a number of invariants, so it's vector. Y can be vector. Then we introduce the goal function as a squared norm of this H of X, of this output, and design speed gradient algorithm is a standard way. And for example, if in Hamiltonian system there is not only energy invariant but some other invariants for mechanical systems, it often happens. Then we may introduce the speed gradient in order to achieve the desired number of values for all the invariants of the system. And there is a result providing conditions for achievement, the goal for control of invariance is our joint result with Anton Shiryaev. And there are several results of such kind, but I do not stop on them. They can be found in the literature. And now I would like to come to the examples. So first example is a feedback controlled Kapitsa pendulum. If we start, if we are interested in control of oscillations, in control of complex oscillatory system, we need to start with pendulums. Even in the pendulums, there are, in control of pendulums, are very interesting and non-trivial problems. For example, the famous case which is attracting attention of researchers up to now, the pendulum which is controlled by changing the suspension point. If you change the suspension point up and down for such a pendulum, then pendulum may behave differently. And what is surprising and very interesting, that if the oscillation of the suspension point are high frequency, so very often we change the point, then it may happen that the upright position of a pendulum, which is initially found first by Stephenson in the beginning of the 20th century, and in the middle of 20th century it was experimentally checked and studied by Russian physicist Pyotr Kapitsa, who later became a Nobel Prize winner in physics. And later, Professor Blechman from St. Petersburg extended these results to other mechanical systems and founded the whole new part of mechanics, which he called vibrational mechanics. Mechanics of the system, which are oscillating by due to external influence, in external inputs, or inside with some internal effect phenomena. So sometimes stability may be achieved for this class of systems in a seemingly unstable situation. But this example, I would like to apply control to this example. And what I want, in the Kapitsa pendulum, the value of control is actually acceleration of the pendulum suspension point. And this acceleration should be sufficiently large in order to, how to say, overcome the gravity. So omega frequency of oscillation should be sufficiently large. My question is it possible to achieve the same phenomenon, stabilize the upright equilibrium with a small control, ideally with arbitrarily small control? It seems that it is not possible. However, if we apply speed gradient method, we introduce the goal function as a squared error in terms of energy with respect to the energy of the upright position. And then we evaluate the speed gradient algorithm and then apply speed gradient algorithm to this problem, then surprisingly we will achieve the same behavior of the system. The pendulum will tend to the upright position in almost all from almost all the initial conditions. And what is most surprising that such a property is achieved with arbitrarily small control level, because gamma, as I said before, for speed gradient algorithms, gamma is positive, but it can be made arbitrarily small. And then the control goal will be achieved anyway. If there is a friction in this pendulum, initially it was a conservative ideal case, but if there is a friction, it can be considered as a disturbance, and we may evaluate the value of the error in this case, and error in terms of energy. This is also was our joint paper with Anton Shiryaev at the beginning of this century. So it was first example. Second example in a little bit different terms, but it's very similar mathematically, because it's a controlled dissociation of the molecule. Two-atom molecule may be described by classical or quantum oscillator equations. In classical equation, we describe it by Hamiltonian, and in quantum case, we describe it by Schrödinger operator. And potential in all these cases is a Morse potential, which has a shape such that it how to say, allows dissociation. Molecule, the bond, chemical bond will be broken. It's possible here, and it indeed applying speed gradient, we may evaluate the control, which may be implemented like some goal, some field applied, external field, electromagnetic field, for example, applied to the set of molecules, or laser field. So it works. It works in simulations, and in quantum mechanical description, it also works. The function, the state of the quantum mechanical system is the function which may, how to say, the probability of dissociation increases. In such a sense, the goal is achieved. And now the next example I would like to show is a selective swinging of pendulums. It is just correspond to the example of experiment which I showed in the beginning of the lecture. Two or more pendulums are suspended from same string or nail, I say, and there is several degrees of freedom, but only one control. The system is underactuated. Such a system was studied in our paper with Mikhail Ananevsky, year 2008, IFA Congress, it was presented. And the result which was obtained here was very surprising. The result is the following picture. Before I formulate the result, I would like to explain why this problem is difficult. Selective swinging, to swing only one pendulum with of several pendulums with one control. It can be formulated as an energy control problem, but there is a restriction, constraint on the energy of the second pendulum. although there is no connection, no link between pendulums, but problem is difficult nevertheless, because first it is underactuated, as I told already. Then constraints are non-convex, and the set of admissible points is unbounded and disconnected. So all the unfortunate conditions are here stopped us from solving this problem. However, the idea of this problem is to apply the penalty function approach, and it works here. We apply, we introduce the goal function v, here it is denoted as a linear combination of two function evaluating the error in terms of two goals, limit asymptotic goals and energy restriction goal. Like here, this should be, the second term should be positive, and evaluating, just a moment, evaluating the speed gradient algorithm, we may try to achieve the goal. And now it's time to make a stop and a little bit discuss a little bit the result. So the result is just a theorem about conditions when the goal of such kind is achieved. And it is just the goal which I suggested you to think about possibility of achieve it in the beginning. And now I would like to ask the question, my question again. How do you think, is it possible to achieve this goal? Maybe now you know that speed gradient algorithm can be applied, but intuitively, what your intuition says? May you give some ideas? So maybe somebody wants to tell the result or ask questions. Now it's time to ask questions also.
So guys, if anyone can comment, Professor Fradkov question, we'll be pleased to hear.
Sorry, am I right that the hardest case would be with the middle pendulum? I mean, so the longest one, the middle one, and the shortest one, and the worst case is about the middle one.
I think the worst case, it is worst case for human. When I myself, I cannot try it. I need to think too fast. I cannot do that. But we are discussing what is possible in principle, what can be done by computer controlling this multi-pendulum system. If there are, say, 2 or 3 pendulum and they all are the same, of the same length, there is no middle. All are the same. And my question was just for this case. Is it possible to solve the problem?
Professor Fradkov, I hope the answer is yes, and with speed gradient, right?
Good idea. Yeah, I agree. But when it is possible, are there some conditions which prevent us from making achieving this goal?
You have more than 20 slides more, so that's not very simple as I predict. I don't know.
Okay, let us pass further. Other slides will related to other problems. And the answer is very simple. Here, the theorem is in our paper of year 2008 is as follows. Yes, it is possible. The answer was correct, but conditions should be, if all pendulums are the same, initial conditions should not be the same. Initial conditions should be different. So the set of initial conditions, when it's possible, is almost all initial conditions. Some manifold of measure 0 is bad. We cannot achieve the goal from the same initial conditions. And I'll show you some simulation results. They were done recently by my PhD student, Bashar Suleiman. And the result is as follows. If we have, look, how big the difference here. Q1 coordinates angle of the first pendulum is 0, initial angle of the second pendulum is 0.01. It's small but not 0. So for some time, these two pendulums, blue and red, go together. They are increasing their oscillation, and then after some time they say goodbye to each other. One goes down, another goes up. After some not big time. And now let us consider a different case when the difference between in initial conditions is much more small. Initial conditions for first pendulum and second pendulum differ by 10 in the power of -5. Very small difference in initial conditions, and this is difficult case indeed. Equal pendulum, identical pendulum, and almost identical initial conditions, and they live together for a long time. But then divorce is appears anyway. But if initial conditions are completely the same, then this picture is not achievable. The separation is not possible. Selective control of such case is not possible. This is interesting, it seems, for me. Now, if there are, we can also consider other questions, restriction for energy of second pendulum from and from below. And the results are also the same with the new goal function. Speed gradient algorithm works, and the angle of energy of second pendulum goes between two levels. And the energy first pendulum goes to the desired value, and speed gradient algorithm works here. Then I would like to tell you a little bit about Lyapunov-Bregman functions. Bregman is, he died recently, unfortunately. He was an interesting student in Saint-Petersburg University, Leningrad University actually, and he suggested a simple method for finding an intersection point for a number of convex sets. In the year 1965, when he was a PhD student. His paper was recommended for publication by Professor Leonid Kantorovich, future Nobel Prize winner. And in the next paper, Blechman improved this convergence and proof and introduced an auxiliary function, which is now known as Bregman divergence. It looks like that. The function, I do not explain this. Picture shows it's very clear. So it functions. This function can be used for formulation of Lyapunov function in proofs, and it is very convenient. And many people since then use this function. They use it in different problems. And this Bregman divergence, Bregman methods, and other terms with the name of Bregman were used in different problems of applied mathematics. And now this paper by Bregman has more than 2,000 citations in Scopus. And the number of papers with the term Bregman in the title exceeds 1,100. So I just give you an idea. I will not go into detail because it's too late already. I'll show you the idea. This Bregman divergence can be used in order to formulate the Lyapunov function for our problems. I call this Lyapunov function Lyapunov-Bregman functions. In case of controlled by speed gradient method, we take the goal function Q and add the Bregman divergence to it. Bregman divergence measuring the difference between theta, current input, and the ideal input theta star. So it's a convex function, can be shown, and it can be used instead of quadratic penalty term in the formulation of Lyapunov functions in adaptive control also. In this case, applying speed gradients, we arrive at the following algorithm. In the differential form, speed gradient algorithm will be almost like before, but the gain will be proportional to the Gaussian of the function h, which we used in order to introduce Bregman divergence. So here the gain is non-constant for adaptation algorithm, which was not, how to say, this case was not studied before. And initial idea was introduced, such a for non-Euclidean algorithm was introduced by Bosch and Slotine in the year 2021. And in my paper, it was extended to finite differential algorithms of speed gradient. I show it here, but I skip these slides and come to the last part of the lecture, speed gradient models of physical systems. So how can we use control algorithm in order to model systems? The idea is as follows. Many models can be formulated from some variational principles. Best, how the least square principle, least other least variational principle can be used to formulate system equation. And here I suggest a new approach for this formulation of system equation. I call it the speed gradient principle. If we have the general form of a system model in the form of x dot is equal to some u, and this U should be found according to some principle. So the principle I suggest is as follows. We introduce some goal functional Q, and under some existing constraints, if any, we evaluate the gradient of the speed of changing this Q according to this equation, and this will be a system model, system equation. It looks a little bit strange, but it works. We may work, for example, with create the first example, a modeling of particle in potential field. We arrived with if Q is a potential energy of a particle, we arrived in this way to the Newton's law, Newton's dynamics law, second law, Newton. And for other more complex cases, also this principle works for wave diffusion heat transfer equation. Such a goal function in the infinite dimensional space works also. For Navier-Stokes equation, also such a more complex goal function can produce such a equation for more complex cases. And what I would like to show you is control of entropy. When in thermodynamics or statistical mechanics, the famous maximum entropy principle, Mach-Cent is by Edwin James, is well known, and it says that entropy grows in the system until it achieves the maximum value imposed under constraint imposed by other physical laws. And the question I would like to pose is that we know how far evolution goes. We know that entropy grows, but how it grows? How does evolution go? And my suggestion, it goes along according to the speed gradient principle. And in some special cases was confirmed by experiment, but in general it is just a principle, just a variation, new variation principle. Entropy principle of speed gradient system evolves in the direction of the entropy speed gradient subject to constraint imposed by other physical laws. It worked, we studied it for different entropies used in applied mathematics. It was published in several places, and I'll show you how it works for system of n-particle systems. You can see here, and it can be found in publications, exact results. It is proved then that energy, that entropy tends to its maximum value. So speed gradient principle, variation principle works. And the last thing which I would like to show you, last new things I would like to show you today is that it can be applied, this speed gradient principle can be applied to study dynamics of the brain entropy. Entropy in the brain, in the human brain. Some people in neuroscience used to introduce entropies, entropy function, studying the brain. It can be measured and evaluated using fMRI devices. And so it's possible, and if it can be measured in several regions of the brain, and it's interesting that in the rest, when the brain is not making any cognitive or physical work, this entropy has some low level. But when our brain start working in a cognitive, with cognitive sense or physical, even physical work, then this entropy goes up, increases. This is very surprising, but this is confirmed by some experiments. But the question which was not posed before is that how it works, how it grows, how fast and in which directions. And assumptions, hypothesis, it is not, which is not confirmed yet, is that it grows according to the speed gradient. It is just a hypothesis. I formulated this, the speed gradient evaluated under some constraint. It's and the law of changing probabilities in the brain between the regions of the brain. I suggest that they change like that. Like that. It is published in a volume of Frontiers Network Physiology dedicated to the memory of Hermann Haken, founder of Synergetics. But at the moment, nobody knows is its value, if this law correct or not. This is just a hypothesis. So we are approaching the end. I just list the other problems, non-smooth problems, which we studied with Maxim Dolgopolik. Problems, control estimation for distributed systems, started with Andreevsky and Orlov and Maxim Dolgopolik also. Oh, they are very interesting, but they are not so simple. And coming to conclusion, I'll say, let me say that I tried to present the main ideas and results of the speed gradient methods. It has been shown to be a useful and efficient tool for solving a wide range of engineering problems and problems in physics also. And for over 40 years of existence, speed gradient method has been used by many authors who applied it to solve a wide range of problems in various fields. So, and some open questions still remain, nevertheless. And for example, concerning convergence of speed gradients algorithms under relaxed conditions, under constraints, we cannot work with general kind of constraints yet. And at this time, let me stop and thank you for your attention and patience. Thank you.
Thank you, Professor Fradkov, for your excellent talk. Yeah, it was really nice to check all the development of the years and some future directions that you gave us. So we are open for questions. Some guys have put some questions in chat. You can do this, or you can open your mic and start the question, right? So if you want to start with this one, Professor Fradkov, you can read this in chat, or you want me?
I think I can read chat.
Okay, perfect.
So there, you can turn on full screen. Yes, I tried, but try to tap onto they. Thank you for help, dear colleagues, to open the screen, but I would like to assumption of first comments by Robert Carlson. The assumptions of Hessian invertibility can be quite restrictive. It typically holds for systems with strictly convex functions, where the Hessian is positive, definite, and invertible. and in non-convex system or those with saddle point of flat region, Hessian may be singular or indefinite, making this assumption invalid. Identifying when Hessian invertibility applies is important for choosing the right optimization methods. I completely agree with this comment. It indeed is a difficult case, and it's interesting to find when this happens for problems for optimization problem, how to choose the right optimization methods. We need to study this. I agree, and that's all. Is that are there other? Yes,
one here.
Another one. Yes, now I can see. Is it possible to use a speed gradient approach for discontinuous mechanical systems? Yes. Here the answer is positive. In our paper with Maxim Dolgopolik, we studied speed gradient method for non-smooth situation and discontinuous functions. It's use idea of subgradient and the approach developed in St. Petersburg by Professor Demyanov and his students, and Maxim Dolgopolik is expert in this area in smooth problems. So at least we have publications, we have results, and if the question is for some specific problem, how to solve it, let us think about this. Maybe let us discuss later. Maybe it is possible. It is not easy, but it's possible.
I have 3 questions from some students. They are a little bit shy. I share this after this one because there is another one here.
Yes, another one. When does almost all condition come from Shirya Fradkov?
Hi, can I get some questions?
Yes, please.
Yes, please. I'm thinking about another one, but please ask, Krisha. I'm listening to you.
At the first, I wanted to say thankful because it's very golden opportunity. I have this meeting. And now I work on extremum seeking. As you know, it's a gradient-based method. Extremum seeking, as you was mentioned in some paper, that the extremum seeking algorithm, like the speed gradient, just inform the gradient of cost functions and to the pool the systems in the optimal points. So I think now I concerned about the external seeking via system with convex system, but is not the symmetric convex system, is not asymmetric convex system. And when the system go up in the optimum point in convex systems and pull off them in the right sides. So I don't find a good solution for external seeking in the asymmetric convex system. There is some idea in the speed gradient algorithm to this kind of system.
It's very interesting question. Thank you for this question. Actually, we never tried to work to apply speed gradient method to extremum seeking problem, and I think that it is possible. In general, it is possible. It's not doubt. It's possible, but I don't know how. But you mentioned the asymmetric problem.
Yeah.
And
I have
maybe this is more
energy systems. The energy system has a symmetric convex system that a very smooth function, and then after the optimal points we have a sharper behavior, that the system pull off the very flat region, and the algorithms can be stopped and stack in the flat region when we use the gradient information to push the systems in the optimal system, optimal points. Sorry.
Well, if this flat area is part of the goal area, the goal may be achieved according to the goal function, but the it doesn't correspond to one point. It may correspond to the whole set. And in terms of the goal function, it's how to say, set of its minima, flat system. So this set, we can achieve this set. It's not a problem, I think. Although we did not work with extremum seeking problem, but I think that it works. In terms of the achievement of the goals, flat set, let us call it flat set, we can achieve it. I think it's not a problem. But what other issues, I don't know. Maybe I don't know intuition enough.
Oh, thank you so much.
Question is interesting indeed.
Yeah, thank you. And I have another questions. It's possible to ask it or in the other time?
Yeah,
can I
please go ahead.
That's okay. Yes.
Now I'm interested to reinforcement learning algorithm that is a very, very famous and well-known algorithm in the world. And there is some algorithm unknown model-based algorithm to find the gradient base in the reinforcement learning or deep reinforcement learning. There is some study or some algorithm speed gradient to use improve the reinforcement learning or not?
Again, good questions. I was thinking that we need to study these reinforcement learning problems, and I hope that something can be done by means of speed gradient approach in this problem, but I do not know answer. At the moment, I do not know the answer. So everyone can start and get the answer.
Oh, great. Thank you so much.
Thank you. Thank you. And here I can see other from
this. I think these three questions, they are at least a little bit related with Karim mentioned about comparing SG with modern data-driven or machine learning approaches. Yeah, if you have done some connections about that, if you have some words about to say, please go ahead, Professor Fradkov.
Yes, the question number one, among the various application areas which you presented, which do you find more promising for future research? Or as for my personal, how to say, interests, I think the neuroscience is most potentially interesting and important problem, because we now see a lot of results and interested in artificial intelligence. And artificial intelligence grows very fast. But not so many people are interested in growing the natural intelligence. But natural intelligence also can be improved. And I think we need to use other tools from mathematics, from computer science, in order to improve natural intelligence. What do you think? I think for me it's very interesting and promising direction of research. So this was the first question. The second, how does speed gradient compare with modern data-driven machine learning? No, as for machine learning is very close to adaptation. Actually, even in the title of our committee, adaptation and learning are coming together. And we use adaptation approach, which are known long before, in order to improve, extend, and make more powerful machine learning methods. So I think at least in our group, we now use machine learning more often than adaptation methods, but mathematics of the methods are very often is the same. Mathematics is very close, and the possibilities of the methods are very close. And in machine learning in modeling natural phenomena. You know, there are so interesting questions. I cannot answer them.
Oh, no.
Yes, they are. Each question is proposing a new area. It's very good audience. You know,
Yeah.
our committee is strong
Yeah.
and interesting. So that's all. Two questions. Okay. Maybe other questions.
Yes. Anyone? Professor Fradkov, I'd like to ask you, this is not so common, but I would like to ask you to give some message to the young guys that they are initiating this area of adaptive and learning control. And what would you say from your history to this young generation?
This is probably the most difficult question. Anyway, I think the good approach is to study mathematics,
Yes.
because if you know, many great scientists of the past knew that. For example, Galileo says that the book of nature is written in the language of mathematics. So if you do not know something in the nature, maybe you need to study mathematics deeper, and then you will understand what you do not understand before, didn't understand before. And in the general terms, maybe this is the most important recommendation. We need to extend, to develop mathematics in order to solve more problems. Even I should say again, to return, I should return to the example of neuroscience. When we study human brain, it is an extremely complex problem to study the brain, because it has about 100 billion neurons. But we actually, even if we knew everything about these neurons, we would not able to deal with this, because it's too complex. So it is important to simplify this complex system and work with some more simple system which encompasses some important features of the initial system. And for such systems consisting of so many dynamical systems like neurons, we do not have good approaches, good results on how to do that. So probably mathematics is some more deep mathematics is needed in order to work with such problems. deal with such problems, I think.
Good advice, Professor Fradkov. So we have 2 more questions in the chat. If you want to read, please.
Okay, the first question, is there an elegant way to deal with almost all initial conditions that the zero speed case is within the invariant set of the Lyapunov function for the asymptotic stability zero speed? Zero speed is almost always the standard starting condition for the controller. Maybe zero speed is not convenient for work of some method, but it is not always this set of zero initial conditions, not always let me formulate it more carefully. Indeed, in oscillatory systems, many mathematical results are applicable for almost all initial conditions. So the set of exceptional points has zero measure. That's true. But if we deal with Lyapunov function and its zero speed set, it not always has zero measure. If the measure of this zero speed set is greater than zero, it's not a good solution. So maybe we need to change Lyapunov function. So maybe need to design something new. This Lyapunov function will not give good results if its zero set has a positive measure. I think so. And is there another question?
Yeah, there is one more. Is there one more asking about the possibility of having partial state measurement if you don't measure fully the state?
Full state. Just a minute. I cannot see this question, but as you said, how to.
What happens with speed gradient approach when we have partial state measurement?
I think speed gradient approach does not provide anything new for this case. All the machinery known in control theory, like observers and filters, it works.
Okay.
It can be, and we have also in my group, we have some results showing what to do if we do not have full measurements of the state. We applied some observers or sometimes adaptive observers, sometimes filters. In neuroscience applications, it's typical because we cannot measure all the neurons, and even in one neuron, we cannot measure all its variables. For membrane potential, for example, is the only thing which can be measured. We use filters and it works.
Sounds good. So, guys, any more questions?
Just one question, please.
Karimi, go ahead, please.
As you know, the same problems between the gradient-based approach is to tuning the gain rate or step parameters. What's the problem with step parameter or gamma in your questions in the speed gradient base?
Excuse me, could you say it again? What is the question? How to change, how to adjust the gain, or what?
Yes, yes.
Huh. Well, how to adjust the gain? What I can suggest, I'm not sure that it works for many cases, but first idea is to consider the gain as a new controlling variable and apply speed gradient to design control for this, for changing this gain. So control the gain by speed gradient.
You choose this parameter or not? Adaptive parameters tuning. Is it possible? Or, yeah, or just it's a fixed gain parameter.
It's possible. I cannot, how to say, mention any publication with it, but I think it's possible. Maybe let me be honest and say that I do not know how to do, but I think it's possible. I think it's possible.
Thank you so much.
Bingo, do you want to ask something to Professor Fradkov?
Yeah. No.
Okay. So guys, I think it's time to finish the presentation. Again, I'd like to thank Professor Fradkov to give this talk. It was really nice, and I think this is the presentation that we have more questions so far since the first one. Yeah, I think there's one more, please. No.
Yeah.
No. Thank you very much. Okay, Fradkov, for your excellent lecture and your kind answers. Okay.
Dear colleagues, thank you all for the attention and for interesting questions. By the way, Bing, can I keep the chat with these questions?
Yes, yes, sure, you can, yes.
Send me, okay. Yes, it's very instructive for me. Again.
Yes, some guys are thanking you. Kevin Moore said thank you so much for this interest talk. So this is all. Thank you, guys. I hope to see you in the next, probably end of this month, right?
Indeed,
and again,
yes.
Professor Fradkov, thank you for sharing your time with us.
Thank you.
Thank you.
Thank
Bye
you.
bye, everyone. Bye.
Bye bye.
Thank you.